Welcome to Brain Vision.
In this problem, we have a ball which is thrown onto a rough floor at an angle of 45 degrees. It then rebounds at the same angle, and we are given the coefficient of restitution between the ball and the floor. We want to calculate the coefficient of kinetic friction between the floor and the ball. We'll firstly look at the vertical components of motion and write down an expression for the coefficient of restitution, E. So between the ball and the floor, the coefficient of restitution can be written as 0 minus v2 sine phi, the final y component of the ball's velocity, over its initial y component of velocity, v sine theta minus 0. The zeros here represent the velocity of the flow, which does not move. And so we see that the coefficient of restitution can be written as v2 sine phi over v1 sine theta. So we'll call this equation 1. So now we have an expression for a coefficient of restitution. We'll come back to that later. The next thing we will do is look at horizontal components of motion and use the principle of impulse and momentum. So the principle of impulse and momentum tells us that the momentum initially, mvx1 of the ball, plus the impulse imparted on the ball during its impact, which is the integral over time of the forces acting on the ball in the x direction, dt, must equal to the final momentum of the ball after it rebounds, mvx2. So we're looking at the x components. So let's write down what this is. So this is simply mv1 cos theta minus the force exerted by the flow on the ball, fx, in a time delta t, and this must equal the final momentum of the ball in the x direction, which is mv2 cos phi. So if we rearrange this equation, we can find an expression for this force, fx, is equal to mv1 cosine theta minus mv2 cosine phi, all divided by the time during which this force is imparted, delta t. And we'll call this equation number 2. Now we'll apply the principle of impulse and momentum again, but this time for the vertical motion of the ball. So again, mvy1 plus all the impulses acting over time, fy dt, so that's in the y direction, must equal to the final momentum of the ball after it rebounds in the y direction, mvy2. So again, let's expand this. So this is mv1, but the y component is multiplied by sine theta minus fy times delta t. Delta t is the same as above, and this is equal to minus mv2 times the sine of phi. So again, we can rearrange this equation and find an expression for the y component of this force, and this is mv1 sine theta plus mv2 sine phi, again all over delta t. We call this equation number 3. Now remember, we are given that fx is equal to the coefficient of friction mu times fy. And using the two expressions above, we can write fx as mv1 cos theta minus mv2 V2 cosine phi over delta t must be equal to mu times Fy, which is m V1 sine theta plus m V2 sine phi, again all over delta t. So rearranging this to find an expression for V2 over V1, we get that V2 over V1 is the cosine of theta minus mu sine theta over mu sine phi plus the cosine of phi. So we have an expression for the ratio of the velocities before and after the collision. We'll call this equation 4. So if we substitute this equation number 4 into equation 1, remember for our coefficient of restitution, we get that E is equal to sine phi over sine theta into this value for V2 over V1, which is cosine theta minus mu sine theta over mu sine phi plus cosine phi. And if we substitute our values in here, we know the coefficient of restitution is 0.6. And so we can substitute theta and phi, which are both 45 degrees. So that's sine 45 degrees over, again, sine 45 degrees. So this is just 1 into the cosine of 45 degrees minus mu, which is still unknown. We wish to calculate for mu, sine 45 degrees over mu sine 45 degrees plus the cosine of 45 degrees, and mu and theta are both 45. So simplifying, we get 0.6 is simply 1 minus mu over 1 plus mu. And so rearranging, we can find the coefficient of friction between the ball and the ground, mu, to be 0.25.